Okay, good morning, esteemed doctoral students. Now, today we discuss into the fundamental pillar of evidence-based public administration, descriptive and inferential statistics. You as future leaders and policy innovators, your ability to understand and apply these concepts is important for crafting data-driven solutions in governance, budgeting, and program evaluation. Descriptive statistics help us summarize and communicate the story that raw data tells. Now, through measure like median, standard deviation, and visual tools such as histograms and box plots. Now, think of it as a think of it as taking the vast complexity of public data, say local tax revenues or satisfaction survey, and transforming it into a clear, interpretable snapshot. Inferential statistics, on the other hand, empower us to move from mere description to decision making. So through applying probability theory, we can infer patterns about entire population based on representative samples. This is the foundation actually of policy evaluation, from testing whether a new e-governance platforms improve service delivery to forecasting public health outcomes using limited field data. With this perspective in mind, let us welcome our presenter who will guide us through the essential methods, application, and nuances of both descriptive and inferential statistics in the context of public administration. Please join me in welcoming our presenter, who will lead us through today's discussion on descriptive and inferential statistics. Take it away, madam.
Dr. Marmelo Abante. Ladies and gentlemen, a blessed Sunday to all of us. This morning, I will be presenting about descriptive and inferential statistics. Statistics is essentially the science of learning from data. In public administration, it's about making sense of numbers to guide better decisions. We divide statistics into two main branches: descriptive, which summarizes the data we have, and inferential, which allows us to make predictions and conclusions beyond the data we've collected. And this sets the stage on how we'll explore both concepts in the next slides. Statistics play a vital role in public administration. It helps us create evidence-based policies, measure program effectiveness, and maintain transparency. Think of it as the bridge between raw data and meaningful public action. Example, it supports policymaking with data-driven insights, monitors and evaluates program effectiveness, ensures accountability and transparency. Descriptive statistics, as per page number 118 of Advanced Research Methods by Dr. Abante et al., summarizes and describes the main features of a dataset. This includes measures of central tendency and measures of dispersion. It doesn't try to make predictions. It simply tells us what's going on in our data test. It summarizes and organizes data, provides a clear picture of collected information, and used to describe characteristics of a dataset. Measures of central tendency. Uy, ba't ganun? Okay. Paano? Ano? Mean average? No. Measures of central tendency: mean or the average, median or the middle value, mode or the most frequent value. Measures of variability such as range or the difference between maximum and minimum. Variance, the average of square differences from the mean. In standard deviation or the square root of variance. Frequency distributions and percentages. This describes how often values occur as to account, or the number of occurrences, proportion or fraction of total and percentages. These statistics help summarizes and understands data sets. Central tendency is a statistical measure that identifies a single value as representative of an entire distribution of data. It aims to provide a precise value that best describes the center of the data set. Here we'll break down each of these points and see how they apply in practice. Average processing time for permits helps identify typical performance levels and supports efficiency benchmarking. Yeah. Validity refers to the spread or dispersion of data points within a data set. It helps understand how much individual data points deviate from the average value. So the common measures of variability includes range, variance, standard deviation, and interquartile range. These measures help assess data consistency, risk, or uncertainty. For example, the variation in service delivery time across districts, measures consistency or disparity in public services, and guides resource allocation. Data visualization tools. So the importance of data visualization lies in its ability to simplify complex data. It makes it easy to understand large data sets and complex information. Also, visualization helps reveal patterns, trends, and correlation that might be difficult to detect in raw data. Likewise, it enables effective communication of insights and findings to both technical and non-technical audiences. More so, visualizations inform business decisions, policymaking, and strategic planning by providing a clean understanding of data-driven insights. Likewise, it helps a story with data, making it more engaging and memorable. By leveraging the data visualization, individuals and organizations can gain a deeper understanding of their data, make informed decisions, and drive outcomes. Example of these tools are bar charts, pie charts, histograms, line graphs for trends, and use in annual reports and presentation. These statistical tools work in real-life public administration scenarios, like citizen satisfaction survey results, mean satisfaction score by department, or variation in responses across regions. Inferential statistics, according to Dr. Abante et al., involves making inferences or predictions about a population based on sample data. Common inferential techniques include hypothesis testing, parametric and non-parametric tests, correlation analysis, and regression analysis. In inferential statistics, one can draw conclusions about a population from a sample, uses probability theory, and common in policy evaluation and forecasting. Key concepts in statistical statistics involves making conclusions or predictions about a population based on a sample of data. These concepts help researchers and analysts draw conclusions based on sample data while accounting for uncertainty and potential error. So example of these are sampling methods and sample size, hypothesis testing, and confidence intervals and significance levels. Sampling is a method of selecting a subset of individuals or observations from a larger population to make inferences about the whole population. By carefully selecting a sample, researchers can make accurate inferences about the population. So we can have random sampling for unbiased representation, stratified sampling for diverse population, or cluster sampling for efficiency. So hypothesis testing is a statistical method used to make inferences about a population based on sample data. It helps researchers draw conclusions based on sample data while controlling for errors. So for example, of hypothesis testing are testing if a new policy provides service efficiency, null and alternative hypothesis, and p-values and statistical significance. Confidence intervals provide a range of values within which a population parameter is likely to lie. They offer a measure of uncertainty associated with sample estimates. Key aspects include confidence level, margin of error, and interval width. By providing a plausible values, confidence intervals help researchers and decision makers understand the precision of their estimates. This could be, we can have as examples, range within the true population parameter like the pulse, 95% confidence that the average wait time is between X and Y days, and helps policymakers assess reliability of estimates. Some techniques that help researchers draw conclusions about populations based on sample data, accounting for variability and uncertainty, includes t-tests and ANOVA for group comparisons, regression analysis for predicting outcomes, and chi-square tests for categorical data relationships. Let's look at some examples so we can see how these statistic tools work in real-life public administration scenarios, like testing if a citizen outreach program increased participation rates, comparing pre- and post-intervention data, and drawing policy recommendations. So in choosing the right statistical techniques, we have to consider the data type, the research design, assumptions, sample size, and objective. In the data type, various statistical techniques are suited for different types of data, such as categorical, numerical, ordinal. Selecting methods that match the data type ensure accurate results. For research design, like experimental or observational, it influences the choice of statistical tests. Experimental studies may require different tests than observational studies. The third, for assumptions, there are parametric tests that have assumptions such as normality, uniformity of variance that must be met for valid results. Researchers should check assumptions and use non-parametric tests if assumptions are violated. So as per sample size, the larger sample sizes increase the statistical power and precision of estimates. Researchers should consider sample size requirements for specific tests and analysis. And as for objectivity, the research objectives determines which statistical methods are most appropriate for addressing the research questions and hypotheses. There are some limitations of statistics, and this includes missing data, bias, and complexity. So researchers may encounter challenges and limitations. So for missing data, the incomplete or missing data can impact the validity of statistical analysis. Researchers should handle missing data appropriately using methods such as imputation or sensitivity analysis. So as per selection bias, measurement bias, or researcher bias, it can distort statistical results. Researchers should employ methods to minimize bias and ensure objectivity in data analysis. For complexity, advanced statistical method may require specialized knowledge or software expertise. Researchers should seek collaboration or consultation with statisticians or data analysts when necessary. So there are some ethics in statistical treatment that includes transparency, accuracy, and integrity in reporting findings. So in transparency, researchers should clearly describe the statistical methods used, including assumptions, procedures, and any transformations or adjustments made to the data. For accuracy, data should be analyzed accurately without manipulation or selective reporting of results to report preconceived hypotheses. Statistical results should be interpreted cautiously, considering limitations, alternative explanations, and potential biases in the data. So as per data sharing, researchers should consider ethical implications of data sharing, ensuring that participants' confidentiality and privacy are protected when sharing datasets. By integrating statistics into decision-making, organizations can make more informed, data-driven decisions, reduce uncertainties, improve accuracy, and optimize outcomes. With this integration, for example, we can come up with develop stock capacity in data analysis, or we can use dashboards for real-time monitoring, or embed statistical review in policy cycles. To wrap up, descriptive statistics summarize, while inferential statistics predict. Both are essential for informed decision-making in public administration, and statistics turn data into actionable insights. So thank you, and that ends my presentation. Thank you very much for listening.
Okay, so thank you so much, no? I just want to play a video presentation which can possibly help, no, the discussions of the descriptive and inferential statistics, no? So wait. So okay, so this will be an additional inputs, no, for the descriptive statistics. Then later on, I will share the link, no, of his YouTube account. I've learned a lot from him, no. So I just want to give you this his videos. No?
Quantitative analysis, one of the first terms that you'll likely hear thrown around is descriptive statistics. In this video, we're going to break descriptive statistics down using plain language and loads of examples that you can approach your analysis with confidence. Let's do it. So let's start by first asking the question, what are descriptive statistics? Well, at the simplest level, descriptive stats, or just descriptives, are a way to summarize and describe relatively basic but essential features of a quantitative data set. For example, a set of survey responses or sales data for a specific product. Descriptives provide a snapshot of the characteristics of your data set and allow you to better understand roughly how the data is shaped, and we'll speak more about this a little bit later. This probably sounds a bit conceptual, so let's take a look at some examples. A basic descriptive statistic could be something as simple as a count of the total number of survey participants, in other words, your sample size. Taking it a step up from there, the proportion of males and females within that survey sample would be another descriptive statistic. Similarly, you could calculate the percentage of people that answered a specific question within the survey and that too would be a descriptive statistic as it describes an attribute of your dataset. These are all very basic calculations, but as you can see, descriptive stats such as counts, percentages, and proportions will give you at least some insight into the composition of your data and help you interpret that data in context. Now, you may have also heard the term inferential statistics being thrown around, and you're probably wondering, how's that different from descriptive stats? Well, simply put, descriptive stats describe and summarize the data itself, while inferential statistics use the data from a sample to make inferences or predictions about a larger population. Put another way, descriptive stats help you understand your sample, while inferential statistics help you make broader statements about the population based on that sample. If the concepts of samples and populations sound a little bit foreign to you, don't worry, we've got an explainer video covering exactly that, and we'll include a link in the description. Now, it's important for me to say that while descriptive stats are relatively simple from a mathematical perspective, they play a really important role, regardless of whether you're using them in combination with inferential statistics or not. There are at least two reasons for this. The first reason is that descriptive stats allow you to quickly identify potential issues within your data set. For example, suspicious outliers, missing responses, and so on. Naturally, it's really important to spot these kind of issues and address them as soon as possible, and so descriptives help with exactly that. The second reason that descriptives are so important is that if you are planning to use inferential statistics, your descriptives will inform that decision-making process. This is because each inferential test has specific requirements or assumptions regarding the shape of the data. If you use an inferential technique that your data set is not suitably shaped for, the results will be meaningless. And so you need to dig into your descriptives to understand what the shape of your data is before you move on to inferentials. All right, with the what and the why out of the way, let's take a look at the most common descriptive statistics. Beyond the basic counts, proportions, and percentages that I mentioned earlier, we have what we call the big 7 descriptives. These can be divided into two categories: measures of central tendency and measures of dispersion. Let's start with the former. True to their name, measures of central tendency describe the center or middle section of a data set. In other words, they provide some sort of indication of what a typical data point looks like within a range of numbers. The three most common measures of central tendency are the mean, the median, and the mode. The mean is simply the mathematical average of a set of numbers. In other words, the sum of all the numbers in a range divided by the count of all the numbers in that range. The median, on the other hand, is the middlemost number in a range of numbers when those numbers are arranged from lowest to highest. Lastly, the mode is simply the most frequently occurring number in a set of numbers. To make this all a little more tangible, let's take a look at a practical example. Here we have a sample data set that reflects the service ratings on a scale of 1 to 10 for a specific business from 15 customers. As you can see, the mean of 5.8 is simply the average rating across all 15 customers. In other words, the sum of all ratings divided by 15. Next, we have a median of 6. In other words, if you were to list all the responses in order from lowest to highest, customer number 8 would be right in the middle, with their service rating being 6. Lastly, let's look at the mode of this data set, which is 5, as 5 is the most frequently occurring rating, appearing 3 times in total. So as you can see, these 3 descriptive statistics, that's the mean, the median, and the mode, give us a quick overview of how customers feel about the service levels at this business. In this case, the descriptives reveal that most customers feel rather lukewarm, and there's certainly some room for improvement. From a more statistical perspective, though, this also means that the data tend to cluster around the 5 to 6 mark, since the mean and the median are fairly close to each other. To visualize this, let's take a look at a frequency distribution of the responses. As you can see, the responses tend to cluster towards the center of the chart from 4 to 7, creating something of a bell shape. In statistical terms, this is called a normal distribution, or a bell curve. As you dive into quantitative data analysis, you'll find that normal distributions and bell curves are very common, but they're certainly not the only type of distribution that you can get. In some cases, data can lean towards the left or towards the right of the chart. This lean is measured using a statistic called skewness. If you look at these three distributions, you can see how different mean, median, and mode combinations will affect the skew or the shape of a distribution. Now, as I mentioned a bit earlier, the shape of your data is really important because it'll impact what you can and can't do in terms of inferential statistics. So be sure to pay very careful attention to the skewness statistic whenever you're looking at a data set. All right, so now that we've looked at some of the common measures of central tendency, let's move on to measures of dispersion. As we've seen, measures of central tendency provide some great insights into how centered a data set is, which is of course very useful, but it is only half of the picture. Beyond centeredness, it's also important to understand how dispersed any given data set is. In other words, how tightly or loosely the data cluster towards the mean. That's the average. This is really important to understand because it impacts how you interpret the mean. If the vast majority of the data are tightly clustered around the mean, then the mean statistic will provide a relatively accurate representation of the center of the data. On the flip side, if the data are scattered all over the place, if they're really dispersed, then the mean becomes a bit less meaningful, and you need to interpret it with some caution. Now, let's put the theory aside for a moment and look at three popular measures of dispersion. First up is the range, which simply measures the difference between the largest number and the smallest number in a data set. Naturally, a high range means that there is at least a possibility of the data being quite spread out, being quite dispersed. But that's not a certainty because it could just be the result of one or two outliers. To get a better picture of that spread, we need to look at another measure of dispersion, which is the variance. And variance measures how much each number within a data set varies from the mean. More technically, it calculates the average of the squared differences between each data point and the mean. If that sounds like gibberish, don't stress. All you really need to appreciate here is that a higher variance indicates that the data points are more spread out, while a lower variance suggests that the data points are closer to the mean. Last but not least, we have standard deviation, which is simply the square root of that variance statistic that we just looked at. Standard deviation serves the same purpose as variance, but it's a little bit easier to interpret because it presents a figure that's in the same unit as the original data. You'll typically present your standard deviation statistic alongside your means when you describe data within your research, because this helps the reader interpret that mean within context. This probably all sounds a little bit conceptual and mathematical, so again, let's look at our sample data set to make things a little bit more tangible. As you can see here, the range of 8 reflects the difference between the highest rating, 10, and the lowest rating of 2. So right away we can see that there is at least some possibility of this data set being quite spread out, as 8 on a scale of 1 to 10 is a pretty high number. We'll skip past the variance and look at standard deviation because these are telling us the same thing. And here we can see that there is a standard deviation of 2.18, which tells us that on average results within the data set were 2.18 away from that mean of 5.8. This reflects a relatively dispersed set of data, which confirms what we can see in the bar chart. For the sake of comparison, let's take a look at another much more tightly grouped, that is less dispersed, data set. As you can see here, all of the ratings lay between 5 and 8 in this data set, resulting in a much smaller range, variance, and standard deviation. You might also notice that the data in this set are clustered toward the right side of the graph. In other words, the data are a bit skewed. If we look at the skewness statistic for this data set, we can see a result of negative 0.12, and that reflects that slight lean. All right, so hopefully these examples help demonstrate how range, variance, and standard deviation all provide an indication of how dispersed a data set is. As I mentioned, these measures are really important because they help you interpret the measures of central tendency, especially the mean, within context. In other words, if your measures of dispersion are all fairly high numbers, you need to interpret your measures of central tendency with some caution, as the data are not particularly centered around that mean. Additionally, as I mentioned earlier, all of these statistics inform what you can and can't do in terms of your inferential stats, but we'll dig into that in a separate video. Okay, so we've covered quite a lot of ground in this video. Let's quickly recap on the key takeaways. Firstly, descriptive statistics, although relatively simple, hopefully you can now appreciate are an essential part of any quantitative data analysis, so don't skip over them in favor of the more exciting statistics. We looked at measures of central tendency, which include the mean, that's the average, the median, and the mode. And we also looked at skewness, which indicates whether data set leans to one side or to the other. And last but not least, we looked at measures of dispersion, which include range, variance, and standard deviation. All of these measures help you understand how dispersed your data are, and in turn, how to interpret your measures of central tendency. If you got value from this video, please do hit the like and subscribe buttons to help more students find this content. If you want to learn more about quantitative data analysis and the research process in general, be sure to check out the Grad Coach blog, where we have a huge collection of free resources, including detailed explainers, how-to guides, templates, and even some webinars. Alternatively, if you'd like hands-on help with your research, check
Okay. Again, statistics serve as the backbone of evidence-based governance. No? For a doctoral scholar, so students in public administration, it offers the analytical tools, no, to transform raw data, whether citizen surveys, agency performance metrics, or the national economic indicators, no, into actionable insights. So through quantifying trends and the relationship, statistics helps administrators move beyond anecdotal reasoning and adopt decision grounded in empirical evidence. As our presenter mentioned, this will be the two pillars of statistical analysis. No? The discipline divides into two complementary branches, the descriptive and inferential statistics. Descriptive statistics na summarize and organize data to show what is happening in a population or program, while inferential statistics extend conclusion from a sample to a wider population, testing hypotheses and predicting future condition. Mastery of both enable public administrators to move from observation to policy and prescription. So the nature and purpose of descriptive statistics, again, our presenter mentioned that descriptive statistics provide a structured snapshot of data through measure of central tendency, dispersion, and distribution. Because in public administration, this might involve calculating the mean turnaround time for processing business permits or summarizing voter turnout rates. These summaries create a foundation for communicating performance indicators to stakeholders, including legislator and public in the public. No? So central tendency in government data is also another concern. No? So measures such as the mean, median, and mode reveal the typical value of a data set. Let's say, for example, the median household income in municipality of Caloocan offers a more robust indicator of economic well-being than the mean when data are skewed by a small number of high-income households. So understanding these measures ensures that policy interpretation are not distorted by extreme values. Dispersion and variability. While central tendency or you mean median mode shows a middle ground dispersion expressed through range, variance and standard deviation, illustrate inequality in risk. A city's average crime rate, let's say, for example, may appear stable, but a high variance could mean that some neighborhoods experience disproportionately high crime, guiding administrator to allocate targeted resources. For the data visualization and communication, again, descriptive statistics become most powerful when communicated effectively. Tables, we use histograms, geographic heat maps allow decision makers to grasp complex realities quickly. Public administrators present such visualization in budget hearings or performance audits, making clarity and accuracy critical for transparency and accountability. So limits of descriptive analysis. We need to understand that there's limits, no, of descriptive analysis. No? Despite their value, no, descriptive statistics cannot establish causality, no, or predict future outcomes, knowing that the unemployment rate dropped, no, by 2%, explain what, but not why or what next. So without inferential tools, administration risks making policies based solely on a snapshot rather than tested relationships. So I just want to play a video presentation again based on inferential statistics.
If you're new to quantitative analysis, one of the many intimidating terms that you're bound to hear being thrown around is inferential statistics. In this video, we're going to break inferential stats down using plain language and loads of examples. Let's do it. All right, so here's a quick overview of how we'll approach this lesson. First, we'll explain what exactly inferential stats are in plain terms. Then we'll look at how inferential stats compare to descriptive statistics. And with those foundations laid down, we'll look at some of the most common inferential tests, including t-tests, ANOVA, chi-square, correlation, and regression. In addition to this video, you'll also definitely want to check out our free statistics cheat sheet, which will help you fast-track your statistical analysis. You can grab a copy of the cheat sheet for free using the link in the description. Also, it's worth mentioning that if you are completely new to statistics and aren't yet familiar with basic terminology such as means and medians and variance, it's a good idea to first watch our descriptive statistics video so that you can get full benefit from this lesson. Again, you can find the link to that in the description. So first things first, what are inferential statistics? At the simplest level, inferential stats, or just inferentials for short, allow you to test whether the patterns that you observe in a data set, a sample, are likely to be present in the broader population, or whether those patterns are just a product of chance. That probably sounds rather conceptual, so let's look at a practical example. Let's say that you surveyed 100 people in a specific city about their favorite type of food. And let's say there were 5 options to choose from. This group of 100 people would be your sample. When reviewing the data, you might find that 40 people selected the pizza option. In other words, 40% of the sample. You could then use inferential statistics to test whether that number is likely reflective of preferences across the entire city. In other words, the population, or that it's just down to chance. More specifically, you'd use a chi-square test, which we'll talk about a little bit later, so be sure to stick around for that. In statistics speak, this question of is it real or is it just chance is known as statistical significance. I won't go down that rabbit hole in this video, but it's useful to understand that this ability to assess statistical significance means that inferential statistics can be used to test hypotheses, and in some cases, they can even be used to make predictions. Now, it's worth mentioning that all of this assumes that your sample is relatively representative of the population, which of course hinges on your sampling strategy. If you're not familiar with samples and sampling strategies, you can check out our straightforward explainer videos which cover these topics. As always, the links are in the description. At this point, you might be asking yourself, but how is this all different from descriptive statistics? Well, at the simplest level, descriptive statistics summarize and organize the data that you already have. In other words, your sample. Inferentials, on the other hand, allow you to use your sample data to assess whether the patterns contained within it are indeed likely to be present in the broader population, and potentially to make predictions about that population. Again, let's look at an example to make this all a little bit more tangible. Let's imagine that you're undertaking a survey to assess customer satisfaction at a local restaurant. Let's assume that your sample comprises a mix of both men and women. If you just wanted to know the average level of customer satisfaction across men and women within the sample, you could achieve this with descriptive statistics. Specifically, you would use the mean statistic. However, if you wanted to compare those two means, in other words, average male rating and average female rating, to see whether there's a noteworthy difference in satisfaction levels between men and women in the broader population, you'd need to use inferential statistics. Specifically, you'd use a t-test, which we'll look at in a moment. So simply put, descriptive statistics describe your sample, and the clue, of course, is in the name there, while inferential stats help you understand whether the patterns that you see in your sample are likely to be present within the broader population. Remember, if you're not yet 100% comfy with descriptive statistics, it's a good idea to watch our explainer video, which covers exactly that. And as always, you can find the link to that in the description. All right, so now that we've covered the basics, let's take a look at some of the most common statistical tests within the inferential realm. Specifically, we're going to look at t-tests, ANOVA, chi-square, correlation, and regression. If you'd like us to cover any other statistical tests, please let us know in the comments. So let's start by looking at the humble t-test. Simply put, a t-test allows you to compare the means, that's the averages, of two different groups to see if they are genuinely different or if that difference is just a product of chance, perhaps because of some outliers or because of very high variance in one of the groups. In other words, a t-test allows you to assess whether the difference between those two means is statistically significant. As an example, you might use a t-test to see if there's a statistically significant difference between the average exam scores of two math classes taught by different teachers. Similarly, you could use a t-test to assess the difference in average plant height when using two different fertilizers. Now, it's worth noting here that there are a few different types of t-tests. In the examples that I just mentioned, we'd be using an independent t-test, which compares the means of two different groups. If, on the other hand, you wanted to compare the mean of one group at different points in time, you'd use what's called a paired t-test. It's also important to understand that each of these t-tests has its own set of assumptions and requirements, as do all of the tests that we'll discuss here, but we'll save assumptions for another video. All right, next up, let's look at another inferential test called an ANOVA. Now, while a t-test, the one that we just looked at, compares the means of two groups, an ANOVA can compare the means of more than two groups at once. Again, this helps you assess whether the differences in the means are statistically significant or just a product of chance. Let's look at an example of ANOVA in action. Sticking with the student theme, if you wanted to assess whether students' test scores vary based on the type of school that they attend, let's say public, private, or homeschool, that's three groups, you could use ANOVA to compare the average standardized test scores of these groups. Similarly, you could use ANOVA to compare the average sales of a product across multiple stores or multiple locations of a retailer. It's worth pointing out that in these examples, we're specifically referring to what's called a one-way ANOVA, but as always, there are multiple types of ANOVAs for different applications, and of course, you need to select the right one or your data will be pretty meaningless. Thankfully, our free statistics cheat sheet, which I mentioned a little bit earlier, makes this task really quick and easy. So be sure to grab a copy of the cheat sheet for free using the link in the description. Next up, let's look at the chi-square test. So while the t-test and the ANOVA test for differences in the means of groups, the chi-square test allows you to see if there's a difference in the proportions of various categories. In statistics speak, the chi-square test allows you to assess whether there's a statistically significant relationship between two categorical variables as opposed to numerical ones. As an example, you could use a chi-square test to check if there's a link between gender, for example, male, female, and preference for a certain category of vehicle, for example, sedans or SUVs. Similarly, you could use this type of test, the chi-square, to see if there's a relationship between the type of breakfast that people eat, let's say cereal, toast, or fruit, and their university major, let's say business, math, or engineering. As you can see, all of these are categorical variables, and so chi-square allows you to assess whether there is a statistically significant relationship between them. If you're not yet familiar with different types of variables, for example, categorical and numerical, then be sure to check out our Variables 101 explainer video. And as always, you can find that link in the description. All right, so now let's kick things up a notch and talk about correlation analysis. Correlation analysis looks at the relationship between two numerical variables, for example, someone's height or weight, to assess whether they move together in some way. In other words, whether an increase in the value of one variable is likely to be accompanied by an increase or a decrease in the value of another variable. In statistics speak, correlation assesses whether there's a statistically significant relationship between two numerical variables. For example, you might find a positive correlation between the number of hours that students spend studying and their average exam scores. Similarly, a correlation analysis may reveal a negative relationship between the amount of time spent watching TV and physical fitness levels. When you run a correlation analysis, you'll be presented with a correlation coefficient, which is also known as an R value. This will be a number between -1 and +1. A value close to +1 means that the two variables reliably move together in the same direction. As one goes up, the other one goes up. On the flip side, a value or correlation coefficient close to -1 means that the two variables move in opposite directions. In other words, as one goes up, the other one tends to go down. Now, it's really important for me to highlight here that while correlation analysis can help you understand how two variables are related, in other words, how they move together, it doesn't prove that one variable causes the other. Correlation is not causation, so be careful to not assume that one variable causes another when you're looking at correlation data. All right, last but not least, let's look at regression analysis. Now, while correlation allows you to see whether there's a relationship between two numerical variables, regression takes it a step further by allowing you to make predictions about the value of one variable called the dependent variable based on the value of another variable or set of other variables called the independent variables. Let's look at an example to make this a little more tangible. You could potentially use regression analysis to predict the price of a house based on the number of bedrooms it has, its location, and when it was built, in other words, its age. Regression analysis of housing data in the area would give you a regression equation that would allow you to plug those factors in other words, the independent variables, to estimate a specific house price, and that would be the dependent variable. In the same way, you could use regression analysis to predict a person's weight based on their height, their age, and their daily calorie intake. Now, it's worth pointing out that in these examples, we've been specifically talking about multiple regression, as there are multiple independent variables. While multiple regression is certainly a popular form of regression analysis, there are many others. So as always, be sure to do your research before selecting a specific statistical test, or grab our cheat sheet to simplify this process. Now, as with correlation, it's important to keep in mind that regression analysis alone doesn't prove causation. While it can help you make predictions, it can't prove that one variable or change in one variable causes a change in another variable. If you want to establish causality, you'll typically need a very specific research design that allows you to control all, or at least most of the variables. You can check out our research design explainer video if you're keen to learn more about that. If you got value from this video, please do hit the like and subscribe buttons to help more students find this content. If you'd like hands-on help with your research project and with your quant analysis, do check out our private coaching service where we hold your hand throughout the research process step by step. You can learn more about that and book a free consultation over at gradcoach.com. Until next time, good luck.
Okay. Inferential statistics address the descriptive statistic limitations by using a probability theory to make prediction or draw conclusions about a population based on sample. This is particularly important in public administration when where surveying every citizen is rarely feasible. Sampling strategies, no, like random sampling, stratified sampling, or cluster sampling help ensure, no, that a subset of data reflects the broader population accurately. Hypothesis testing for policy evaluation is important, no, because hypothesis testing allows administrator to determine whether an observed change, no, such as reduced processing time after implementing an e-governance platform is statistically significant or merely due to chance. No, tools like t-test, as our video, no, discussed, chi-square or chi-square test, and analysis of variance are commonly applied in policy impact studies and program evaluation. Estimation and confidence interval is also another consideration. Beyond hypothesis testing, inferential statistics provide point estimates in confidence intervals. For instance, no, most commonly a 95% confidence interval for average commute time provides a range in which the true population mean likely falls. No? This quantification or uncertainty is essential, no, when presenting findings, no, to policymaker who need both precision and an understanding of potential error. There are somebody who discuss correlation and regression analysis, but again, correlation measures the strength of relationship between variables, while regression goes further to model how an independent variable influences a dependent one. So a public administrator might use multiple regression to assess how factors such as education level, health expenditure, and employment programs jointly affect poverty reduction, helping prioritize intervention. So time series analysis actually is indispensable for budgeting and planning. No? Techniques such as ARIMA models can forecast future demand for social services or predict economic trends affecting local tax revenues. Reliable forecasts enable proactive decision-making and resource allocation. Integrating descriptive and inferential approaches like real-world policy analysis blend the two branches, no? A doctor in public administration researcher, or you as a researcher, may evaluate, no, a disaster response program. Might first use descriptive statistics to profile affected communities, right? Then, right after that, apply inferential methods to test whether the program significantly improved recovery times compared with control region. And this combined approach ensures both clarity of current conditions and rigor, no, in causal inference. No? Data quality and ethical consideration must also observe. No? Both descriptive and inferential statistics depend on high quality and take note ethically collected data. No? Ang dami kasi dumadaya ng data. No? Let's say sila rin nagsasagot ng kanilang survey, or 5 times pinasagutan yung survey sa isang tao, no? So, public administrator must guard against bias, missing values, and privacy breaches, especially under laws like the Philippine Data Privacy Act of 2012. Ethical stewardship of data maintains public trust and syempre ensures that statistical conclusions are legitimate. So, we have a lot of practical tools for doctoral research, no? Advanced software such as R, Python, Stata, or Stata, no? SPSS, the most commonly used, allow you as doctoral candidates to conduct complex analysis and produce reproducible results. Visualization tools like Tableau and Power BI, most commonly used, no? Translate statistical findings into compelling dashboard for policymakers and citizens, bringing the gap between technical analysis and public communication. So there is certain implication, no, for doctoral practice and policy. For doctor in public administration scholar students, mastery of descriptive and inferential statistics is more than an academic requirement. Ano po? It's very important because during our undergraduate and master's degree program, we are always rely with the statistician. They just explained with us the results, no? Showing us the tables, then the discussion or description of the table, without knowing on how they will be able to come up with this result. No? So as doctoral in public administration student, it is needed, no, because it is a leadership skills. Without evaluating the fiscal impact of national program, forecasting demographic shifts, or crafting data-driven legislation, these statistical methods empower administrator to design policies that are transparent, equitable, and grounded in the robust evidence. So before I forget, no, thank you so much to our presenter for that comprehensive discussion. And again, let me now synthesize and extend the key insights of our doctoral lens. No? So again, descriptive statistics serve as a foundation of any policy statistics. Ano po, me, no, before, it's too hard for me to understand stat, no? But again, we need to understand that, wait, hold on. Okay. We need to accept the fact that this statistic is the grammar of data, no, helping us make sense of the numbers that shape our daily decision. And in public administration, no, data without statistics is just noise. No, with these statistics, no, it becomes the foundation policy. So, again, as I mentioned, no, the descriptive statistics employ measure of central tendency, mean, median, and mode to locate the center of data sets, and measures of dispersion, range, variance, and standard deviation to reveal variability. No? Let's say, for example, if we analyze the monthly income of household in Caloocan City, a median income of 20,000 provides a clearer picture of the typical household than a mean skewed by a few high earners. Graphical tools like frequency distributions or heat maps are invaluable in public sector dashboards, allowing decision makers to instantly grasp patterns such as spikes in emergency room visit or fluctuation in taxation. Inferential statistics extend this foundation to prediction and policy testing using sampling methods, random, stratified, cluster. Bibihira po ipagamit sa atin yung yung isang other methods na depend po kung quali ang ating study. But in quantitative methods, we normally use random sampling, stratified sampling, or cluster sampling to ensure that a manageable subset of the population accurately represent the whole. No, techniques like confidence intervals quantify uncertainty, while hypothesis testing, t-test, ANOVA, chi-square, evaluates whether observed effects are statistically significant. So let's say, for example, no, when assessing whether a new digital permitting system reduces processing time, an ANOVA, no, can compare average wait time across different municipalities to confirm if improvements are not due to chance. Similarly, regression analysis help estimate the effect of independent variables such as education level or internet access on outcomes like voter turnout, enabling evidence-based allocation of civic education resources. So in public administration, these tools have direct impact during budget hearings. Descriptive summaries make complex fiscal data comprehensible to stakeholders. So during program evaluation, inferential tests justify whether to scale, to revise, or discontinue initiative. A case in point, the Philippine Statistics Authority routinely uses stratified sampling and confidence intervals to project national underemployment rates from regional surveys, which then guide labor policy. So, the synergy of descriptive and inferential statistics transform raw numbers into actionable knowledge. No? Descriptive techniques illuminate what is, inferential techniques predict what could be. No? Together, they empower public administrators to craft policies that are not only well-informed but also scientifically dispensable. So, an essential competency for leaders dedicated to transparency, accountability, and effective governance. Ano pa? So as I mentioned earlier, this statistic is the grammar of data, no, helping us make sense of the numbers that shape our daily decision. Every swipe of a transit card, every online purchase, every weather forecast is statistics at work behind the scene. No? From predicting traffic patterns to planning city budgets, statistics turns road facts into informed action. Whether we check a product rating or a medical report, we rely on statistical evidence to guide our choices. A statistic is not just for researchers. Take note of it. It is the silent partner of everyday reasoning, from setting insurance rates to tracking a child's growth chart. No? In public administration, data without a statistic is just noise. So with the statistics, it becomes the foundation of policy. Every news headline citing percentage or polls is a reminder that these statistics frames how we understand the world. No? Statistics transform uncertainty into insights, making complex realities understandable and actionable. So from election results to the average rainfall forecast, statistics connects personal experience to societal trends. Good decision, whether in government or at the grocery store, begin with accurate statistics and truthful interpretation. So I think that's it for this topic. Thank you to our presenter.